Hi, Kacper.
Hello.
Long time no see, right?
Yeah, it's been like 2 months. I'm not sure if we are going to keep the pace, but definitely we need to think about another project just to
Yeah,
present
hopefully.
something before the end of the year.
So, what do you want to show us today?
Yeah, last time I was speaking about Qdrant, which is a vector database, but somehow I feel that we missed a huge part of designing such pipelines. Because similarity learning is the typical way of creating those pipelines to be able to perform the neural search. And we actually found out that there was no existing framework for similarity learning, which is slightly different to the classical machine learning, like classification of regression. So we designed one. And today I would like to present Quaterion, which is a separate tool, but goes pretty well with Qdrant.
Yeah, sounds quite interesting.
Yeah, I've prepared a demo just to show how we could use it. But if you are familiar with PyTorch Lightning, then things should be pretty easy because we are PyTorch Lightning based. So we just decided to go for a really simple tool that everybody could just easily adapt to. So I think I could just share my screen just to present what I prepared for today. Here is the notebook that I prepared for today. I just downloaded the data from Kaggle. The wine reviews Kaggle data set is quite interesting and is pretty good choice for creating a basic recommendation system, especially for those ones of you who are really into wine and who would like to become more experienced and just feel the taste and smell a bit better. Here is how this data set look like. Basically, it contains some attributes like the variety, some region information, but also the textual description. And this is kind of interesting because this was written by some real people and scraped from typically from Twitter. So this is like the description of the wine. What you should feel if you drink it, how it should taste like. And basically that is kind of interesting because that is built from over 100,000 of reviews. So, well, actually nobody can drink that much wine. That's impossible. I know that some people try to do it, but that won't end up well. But if you would like to have a system that will suggest you to buy a specific bottle of wine because you like some different ones, there is a great room for using similarity learning. But just to start simply, actually, similarity learning is typically based on some neural embeddings. So this is fairly simple. We have a deep neural network, typically transformer based, and we use like a temporal state of one of the hidden layers as some kind of a different data representation of the input examples. So we encode some non-tabular data like text or images, sometimes videos or audio signals into an embedding space, into a form of specific dimensionality, vectors of specific dimensionality that we can easily compare to each other. And that's the thing. We have a lot of available pre-trained models that we can just use out of the box, but there is an issue with transferring that knowledge from domain to domain. If you just use a BERT-based model, it was trained on a specific data set, but if you work, let's say, in healthcare, then the terminology might be a little bit different than the general one that was used to train this original model. But that doesn't necessarily mean you cannot reuse it somehow. And that's where the similarity learning comes to the rescue. Quaterion, that's the library that I would like to present today, allows you to tackle those pitfalls that you may face while working on similarity learning. We simplified the whole process of designing such network. And that integrates pretty well with PyTorch and PyTorch Lightning. So in case you use it, you can just still use your models in the same way like you did before, but just fine-tune them a bit differently. Okay, and what is the idea? If we just took those original embeddings from the pre-trained models, which are available from Hugging Face, for instance, but there are also some other projects that just expose those pre-trained models. Points marked with the same color should belong to the same class, and they are quite well distributed. But there are also some points that should be probably closer to the other examples from the same class. And the goal of the similarity learning is to adjust the vector embeddings to be a bit closer in the space, somehow to tidy the space up. So all the points belonging to the same category will be closer than they were originally. And it doesn't apply to classes only, but if you have any preferences, like you would like to have some specific points closer to each other than they are in the original space, similarity learning is the answer. In our case, imagine you drink quite a lot of wine and you mark every single bottle, either I liked it or I hated it. If we had this original descriptions taken from the Kaggle data set, they won't cover your preferences at all. They will only capture the semantics of the description, but nothing really else. And the goal of this notebook will be to adjust those embeddings a little bit, so all the preferred wines will come closer in the new space, but in the same time, we would like to keep the original information encoded in those vectors. So this is not about making a mess in that space again, but rather about slightly moving the points closer to the other members of the same class. First of all, we of course need to start with some embeddings, and in order to do that, we are going to use sentence transformers. This is a library which is publicly available and of course exposes a lot of pre-trained textual models, so we can use them directly. And this is fairly easy. We can just retrieve some descriptions and create the embeddings for them using the encode method. But this is not the final process. Of course, we could start right away, compare those vectors just to find some similar examples. But we would also like to cover our own preferences and include them into those embeddings somehow. So we need to define a pipeline. Let me just briefly describe what is the pipeline going to look like. Basically, if we took a neural encoder, which is like part of this original transformer, it will produce some sort of embeddings. And our idea is to attach some new head layers at the end of this original network and just fine-tune the whole network in order to have some new embeddings, which will be slightly different to the original ones. So the whole process starts with a specific data point. Here, I assume that will be image, but we are going to work on text. And then it goes through this original transformer and then through our head layers that we attached into it. And that's the whole pipeline. But at some point, we realized the typical approach is a bit different, because if we take an existing encoder, an existing transformer model, the approach might be to attach some new head layers, but then train only those newly attached layers and keep every other existing layer frozen. So we won't be changing weights in this part of the network, but only applying the weights in this head. And we found out that there is a huge room for improvements here, because if we put those images or text through this encoder, then everything becomes deterministic. there is no point to just go from the raw data and process it through this transformer network again and again in every single epoch. Instead, we introduced a caching mechanism, which is quite a unique feature that puts those original embeddings into your GPU or CPU and then just train the head of the network in separation without even calculating those embeddings again. So this is a one-time process that allows us to speed the things up and make this similarity learning more easier and less time consuming. So how is it implemented? There are like three major concepts in Quaterion. The first one is the encoder. An encoder is a part of the network that produces the embeddings. Here we just need to define some structure, which is a transformer and a pooling layer, and also define some properties of that model. This is quite similar to the structures of PyTorch Lightning. So if you are familiar, you are probably going to see it quite easily. We need to define the embedding size, and one important step is to provide a function that will convert the input samples into the tensors, and that's basically it. This is like the basic structure of the encoder that allows to put any transformer we want, so any pre-trained model we would like to use, and then just test some different, perform some different experiments using some different networks. Another important concept is a trainable model. This is similar to a Lightning module in PyTorch Lightning. Here we need to configure some metrics, optimizers, define a loss function, and configure the encoders. That's the major difference. Here we just select the transformer to be used on the original data and build the encoder so it may be configured by the model during training. We also need to provide a head. Here I decided to use skip connection head. This is to avoid the forgetting of the network. So we are going to use a skip connection in order to provide this original embedding to the output layer as well, so it won't be forgetting all the stuff and starting from a random point, but it will be just able to reuse this original embeddings. We have quite a great article describing why it's helpful, so I will just put a link into the description of that video. And we also need to configure cache mechanism. This is fairly simple. We can decide the type of the cache, but auto works pretty well, and the batch size. And this cache is going to automatically put those computed embeddings into your GPU or CPU, depending on how you train on network. And that's going to increase the performance of the training phase. The last important thing is to define the data set. As I said, we would like to incorporate our own preferences into that embeddings, but I have to admit I am not like a wine expert, so I decided to choose a different way. I decided to choose some specific varieties of wines. As you may see, I rather prefer white wine. And just select a list of wines that I liked. This will be like a sample of 50 points from this original data set, and the same for the ones that I hated. Just to see, here is just a list of the descriptions we selected. And that's where the magic happens. We also need to define the third element, which is the data set. And the data set will consist of those textual descriptions of wines and the name of the group they belong to. So here I provide both lists of those ones that I liked and those ones that I hated, and build a list of examples with this additional group name at the end, because the data set is going to expose a similarity group sample, which is defined from this textual description and the ID of the group it belongs to, because the whole idea is to create two separate groups, one to the wines that I like, and the other ones to the ones that I hate. And the training will go in the way that it will try to make those embeddings of wines that I like closer to each other. But this is also quite a standard way if you are familiar with PyTorch Lightning. And now we just need to train the network. So for that, we are going to create an instance of the PyTorch Lightning trainer. We are going to define the data sets and data loaders for training and validation parts. Here I just divided this original data set into two separate pieces. 80% will go to the training data set, and missing 20% to the validation data set. And by running the model, I can just train it to just adjust those embeddings. As you may see, this whole cell executed below 6 minutes. That means that I was able to train 300 epochs in just 6 minutes using this data set, because that's the huge advantage of that approach. Because we cached all those embeddings, we could reduce the time spent on the training phase, because it was not required to process the original text through this transformer, because it became deterministic. This is also quite well visible here. We have almost 23 million of parameters, but only 150K are trainable. So we are just training a part of the network, and there is no reason to use the missing parameters at all during the training phase, if that's just deterministic. Okay, and that was actually all. We were able to train a network in quite a short time, I have to admit, and right now we could try to verify if that really changed anything. And for that, we are going to perform a neural search. Probably I should have used Qdrant to use it, but since we are
why not?
Yeah, but since we are still experimenting, it was like pointless. I'm not going to use that in production, but so I decided to just go with some utilities from sentence transformers. But let me maybe rework that notebook, so we will use Qdrant instead. That's a good point. Basically, what happens here, we just select 5% of all the descriptions for our data set, just to avoid calculating embeddings for over 100,000 examples, and then prepare a query. And the query will be, I would like to have a wine with floral notes with a touch of pomegranate, and perfect for summertime evening meal. That's my query. If I would like to choose a wine for today evening, maybe I could type this description. And if we use this original embeddings, here are the results. The top 5 entries from this dataset sample. It's quite easy to see that those fruits that we selected are just directly put here in the description. So that worked pretty well. Here, summertime meals, so exactly what I typed. So that worked pretty well. And we have like 5 examples using the comparison of their descriptions. But if we did the same with our fine-tuned network, that's also the same process. Here is how the results look like. So the first wine that was chosen is exactly the same one. But if we just compare the score that was achieved, there is a subtle difference. Mostly because we decided to reuse those original embeddings and just wanted to adjust them slightly to our preferences. And that means that those results are quite similar, because here we have the same wines being selected, but there is a bit of difference at 3rd and 4th position. because here our fine-tuned model decided to score them differently, because it assumed that we will like this this one a bit more than the other. And that was actually the goal. We didn't want to like break things and forget everything from the original embeddings. We just wanted to adjust their position in space a bit, so they will encode not only the textual meaning of the textual description, but also our own preferences. And that could be actually anything. If you have some examples like this, you could build a recommendation system. But let's say if you were only able to label a small part of your data, then that's also a quite interesting approach, because you could directly use those embeddings to encode some properties of the objects you work on, and then apply the similarity learning only on that part, on that small part of the data. So it will capture the similarities between them and the differences as well. So then by simple voting, like in KNN, you can select the most probable class. So similarity learning reduces the data requirements a lot, because here for that example, we just used like 50 positive and 50 negative examples. So this is the amount that I could probably label within just 10 minutes or so. And that should be enough in many cases. So definitely similarity learning is a way to go if you can't afford, or if that's even impossible, to label a huge amounts of data. And that's what makes it different to this traditional approaches to machine learning. And that's also the reason why I really liked it.
Yeah. And I guess the reason you were doing this is because the users of Qdrant, they had to come up to reinvent the wheel every time for all the use cases, right? And then you just wanted to show them a unified way of coming up with vectors before you put them into Qdrant, right?
Exactly. Yeah, this is exactly the purpose, but not only for Qdrant users, because we know
For
that there are
other,
plenty.
yeah, exactly. For others vector search databases that should also
Exactly.
work, right?
Of course, we will try to convince you that Qdrant is the best choice, but definitely if you use any other tools, then this is also possible. This is not like tightly coupled with Qdrant, so feel free to use it for anything that requires similarity learning to be used. We are not going to like merge those tools together. This is a separate project, of course.
And how many people work on this?
Well, there is about 12 people on board in Qdrant, but Quaterion was developed by our data science department. So not necessarily by people working on the Qdrant, which is Rust based. I would say there are like 3 or 4 contributors to that project from Qdrant, but we actually got some external contributors as well. So definitely the number might not be that accurate.
If somebody wants to become this external contributor, so how do they go about this?
Well, perfectly, I would suggest to join our Discord channel, where we communicate about our tools. There are also some issues available on our GitHub repository, so that might be a good starting point. But also, as usual, I encourage you to just give it a try. And if you see something that doesn't work as you expected it to, or if you see a better way of doing different things, please just let us know, either on by creating a GitHub issue or by providing some feedback on our Discord channel. We are just looking for some adopters of that framework, and we already have some.
Can you show us how to find your Discord channel? Is there a link somewhere on your GitHub?
There is a link on our website. We can also put a link to the description of that video. So that would be the best way. But if you just go to quadrant.tech, there will be a link to the Discord community under in the main menu. So that's quite easy to be found.
And do you have any advice for anyone who is watching this?
Yeah, I really encourage you to start using similarity learning as some sort of first choice if you work in a small or medium-sized companies, because the thing is that those smaller players cannot afford creating huge system, but that's a great way to reuse something that has been already trained on some huge machines, some bigger networks that you can't probably afford to train on your own. And that also is a great way to reduce both the time spent on annotating the data and the time spent on the training if you just utilize the powerful mechanism of similarity learning and the cache mechanism that we offer. So that's a great way to reduce the time and the cost of your projects. So definitely that's an interesting branch.
Mm-hmm. Okay, thanks a lot. Thanks for the demo. Thanks for showing something else second time. I'm really looking forward to seeing new things from you. So maybe you will have something else in a couple of months. If not, maybe later, but you're always welcome to come and show what you work on. So thanks again for doing
this. Thank you,
this.
Alexei. That was really cool to be here again, and definitely we need to think about the next project because there's plenty of work to be done in that area still.
Okay, thanks.
Thank you.